Hey, welcome to a little video which we're calling Page 20, and this is an example of why the fast Fourier transform works, and in particular how the divide and conquer idea works. Okay, let's just pause. Okay, so we're going to do the example with n equal to 8. So we're really just doing polynomial interpolation. Oops. Like we talked about with the method of undetermined coefficients, but it's in a weird world. In a weird mathematical world where alpha to the 8th is equal to 1. That'll come up later. But what we've seen is we're in a special interpolation case where we're taking each xk is equal to alpha to the k. So the values, the points we're interpolating are alpha to the 0, y0, alpha to the 1, y1, and so on, up to alpha to the n minus 1, y n minus 1. So we want the polynomial, we want the coefficient c that will interpolate that polynomial. So if we write out what those things mean, the column J, so row K, column J of the matrix F8 is equal to, in fact it's true for any n, is equal to alpha to the kj. So if we write that out laboriously, so we've got row 0, 1, 2, 3, 4, 5, 6, 7, oops, just 7, and column 0, 1, 2, 3, 4, 5, 6, 7. So the coefficient matrix will be multiplied by the coefficient C0, C1, C2, C3, C4, C5, C6, C7, giving the right hands their y values, y0, y1, y2. This is really laborious. 4, y5, y6, y7. And that's not the half of it. The hard part is writing out these. So we just raise alpha. So this row is alpha to the 0, alpha 0, alpha 0, alpha 0, alpha 0, alpha 0, alpha 0. So those are all to the 0 because it's row 0 times each column j. They're all alpha 0. And similarly, if the k in this formula here is equal to, if j is equal to 0, doesn't matter what k is, these are all alphas to the 0. And of course, alpha to the 0 is just 1. Now in row 1, it's a little different. So when k equals 1, the values are just alpha to the column number. So this is just alpha 1, alpha squared, alpha cubed, alpha the 4th, alpha the 5th, alpha the 6th, oops, alpha the 7th. Excuse me, I had to sneeze. Okay, and now row 2, it's alpha squared times j. So this just gives you alpha squared, alpha the 4th. So to go from one column to the next, we just multiply by alpha squared until we get up to alpha to the 14th. And this one, it's cubed. So cubed, 6. So we're just adding 3 to the exponent on each step. Alpha to the 12th, alpha to the 15th, alpha to the 18th, alpha to the 21. And here it's alpha to the 4th. So we're adding 4 to the exponent on each step. And this really is just this formula when you work out what it gives you. Whoops, alpha to the 28th. And then here we get alpha, the factor is alpha to the 5th. So it's alpha to the 5th, alpha 10th, alpha 15th, alpha to the 20th, alpha to the 25th, alpha to the 30th, alpha to the 35th. Then we have alpha 6, alpha 12, alpha 18, alpha 24, alpha 30, alpha to the 36, alpha to the 42, And finally 7s, alpha 7, alpha 14, alpha 21, alpha 28, alpha to the 35th, alpha to the 42, alpha to the 49th. So that's pretty disgusting, you've got to admit. So what? Well, the interesting thing here, let's move on to the next page. Okay, the interesting thing here is if we rearrange those numbers, we rearrange them into the even columns and the odd columns. So I dread doing this, but I'm going to anyway. So let's see. Just getting the basic blank area laid out. Okay, so the odd columns, the even column, the first one is alpha to the 0. Alpha 0, alpha 0, alpha 0. Okay, and then we have the alpha squared. So basically the even columns is alpha squared, and then what? So it's, oops, my mistake. So we gotta rub that out. So this is alpha 0, and then we have alpha squared, and we should have noticed that I didn't point it out at the right time, that the rows and columns are the same in this matrix. So I'm just going down the column multiplying by alpha squared each time. And then the next one is alpha 0, alpha to the 4th. So here on this one I'm multiplying by alpha to the 4th. So it's alpha 8, alpha to the 12, alpha to the 16, alpha to the 20, alpha 24, alpha to the 28, and finally alpha 0, finally for the even columns by 6. Alpha to the 12, I don't know why that did that. Alpha to the 18th, alpha to the 24th, alpha to the 30th, alpha to the 36th, alpha to the 42. Okay, and that ends the even columns, and the odd columns is the first one is alpha to 0, alpha cubed, alpha 6, alpha 9th. Right? No, it is not. The even column, the even columns are alpha, just multiplying by alpha. So it's alpha 4, alpha 5, alpha to the 6, alpha to the 7. That's column 1. Right, so this is column 0, 2, 4, 6, and this is column 1, 3, 5, 7. So in column 3, it's alpha 0, alpha cubed, alpha to the 6, alpha to the 9th, alpha to the 12th, alpha to the 15th, alpha to the 18th, alpha to the 21, and column 5 is alpha to 0, alpha to the 5. So we're just going by tens. I'm sorry this is so painful for me and you, no doubt. The bad thing is we don't have enough space to really make the point. So just you may have to hop back and forth between the different slides. Oops. Alpha to the 35th, alpha to the 42nd, alpha to the 49th. Okay, now if we rearrange the columns to keep the same system, it turns out we must rearrange the variables. So we get the first half of the variables are C0, the even ones, and then we have the odd ones, C1, C3, C5, and C7. But those are equal to the same right-hand side values. 2, Y3, Y4. So we've just rearranged the columns, which means rearranging the variables. If you think about what your augmented matrix system says, All right, now we're going to actually want to move this up and back and forth, so I don't know how that's going to look in the recording, but let's give it a try. Oops. So this system is saying, so let's see, pause there for a moment while I take a... Okay, we're ready for the divide and conquer idea, so let's look at this more carefully. All right, what's the point of looking at the matrix broken into these pieces? Well, matrix multiplication says, oops, put the pencil. So matrix multiplication says we're going to take this matrix, the upper half size matrix, times this vector plus this matrix times this vector to get this right-hand side value. And similarly, we're going to take this matrix times this vector plus this matrix times this vector to get this vector. So that's what's the point of doing divide and conquer is it turns out we really only have to multiply this special matrix by each of these two to get all the answers we need. So in fact, we can do two half-size multiplications. Which leads to the recurrence relation that f of n is equal to whatever f is the number of multiplications to the Fourier transform is equal to 2 f of n over 2 plus some multiple of n, some number times n. So to see that that's true, let's just take a look. I'm going to try some arrows here. Is this the arrow? No. Is this the arrow? Okay, I don't know what this little thing is that I put in there. It won't go away either. Oh well, sorry. So if you look at this matrix and the one next to it, and I'm not going to rewrite this because it's actually a very obvious fact if you accept that these are all zeros. So check out this row versus that row. They're the same, yay. Now how about, the question is, what could we multiply this row by to get this row? If you think about that, obviously this first element, alpha to the 0, is just 1. So what would you multiply alpha 1 by to get alpha? And the answer is alpha. So what would you multiply alpha squared by to get alpha cubed? Well, that's alpha also. So in fact, it works beautifully. Each of these four, if we multiply each of them by alpha, we get the corresponding row in the upper half. And this is true, and here we have to multiply by alpha squared. So alpha to the 4th times alpha squared is alpha to the 6th. Alpha to the 8th times alpha squared is equal to alpha to the 10th, and alpha to the 12th times alpha squared is 14th. And that's true all the way down for all the rows. And the numbers that appear in this first odd column are the multipliers. So that's a really big deal. And it's kind of obvious from just the format of this coefficient matrix. So that says that we can multiply this matrix, which I'm going to call F4. So let's give names to things. This is F4, and let's call this guy here V, and let's call this little half-size vector W. Okay, so on the next page, okay, so what's going on here is, this may be hopelessly muddled. So we need the connection between these two, and that's a really big deal. So this is where we bring in alpha to the 8th equals 1. So because alpha to the 8th equals 1, this matrix here is in fact also F4. So let's take a look at that. So if you take every one of these, it's real simple. Every one of these numbers, if you just throw away all the 8's in the exponent. So this is alpha 0, alpha 0, alpha 0, which is the top row. If you throw away the extra 8, so any 8 alphas multiplied together, this is 10 alphas multiplied together, and the first 8 all collapse to cancel each other out, just give us 1. So this is just alpha to the, this is just alpha squared, which is exactly what we see up here. And this is alpha to the 20th. We take away 16 alphas and we're left with 4. And here we take away 28 alphas. We take away 24 and we're left with 6. So you can check similarly that all of these values down here, if we reduce them using this big fact, is exactly equal to the upper thing. Okay, now since this matrix could be obtained from this matrix by multiplying each row by these numbers, that means since this matrix here and this matrix here are the same, that means this matrix multiplied by those numbers also gives us the correct thing. So now I'm going to jump ahead. I hope I haven't screwed this. What we're seeing is that we want F4 times V plus F4 times W, but these guys are adjusted. So however you want to say it, I'm going to just say multiply the row J by alpha to the J. So we take the F4 matrix and multiply each of its rows by the power of alpha, 0, 1, 2, 3 for this half. And that'll give us Y0, Y2, or Y1, Y2, and Y3. So that's our first equation. And the second equation for the second row, if we hop back for a second, I don't know if that'll work, let me just write it down. The second one says, oops, yeah, we gotta go. Okay, so what we have seen is that therefore F4 times V repeated, so we only need to calculate that once. And it's the same multiplier factor times F4W is the second one. So, but these multipliers are alpha 0, alpha 1, alpha 2, alpha 3. These multipliers are alpha 4, alpha 5, alpha 6, alpha 7. Okay? And that gives us Y4, Y5, Y6, and Y7. So if you look at concrete examples, it's perhaps easier to see. I just wanted to go through the more general case. So I've given you the on the answers to the sample test in class, the answer to problem 6 on the sample test, and that's a concrete example of all this going on. But maybe this will help. Let's see. So I think that's all I have to say about generically the fast Fourier transform and why the divide and conquer trick works. So let's call it a day. And the next video I'm going to do will run you through computing the inverse of a fast Fourier transform matrix.